Hey everybody, Dr. A here, and in this video we're going to be exploring an example of angle of twist with a torsional spring. So let's look at the given information. Here we're being asked to compute the angle of twist of end A, which is this free end here. We're being told that the polar moment of inertia is 10 inches to the fourth, the shear modulus is 4,000 KSI, and the connection is flexible with a stiffness, a spring stiffness or a torsional spring stiffness of 120 kip inches per radian. So we see this connection here, it's kind of fixed but not completely fixed because it has some flexibility to it. So when you apply this 30 kip inch torque at the end A, at the end of this 48-inch long shaft, what's going to happen is the cross section of the shaft itself is going to twist, of course, but this connection back here, these slotted bolt holes, will also tend to rotate some based on this flexibility of the connection. Okay, so how do we solve this problem? Well, we know that angle of twist of a shaft is equal to TL over JG, and we know we have one segment here, it's 48 inches long. We know that the applied torque, the only applied torque is 30 kip inches, and so we know that T is just going to be that 30 kip inches, right? We know J and we know G, but we have this flexibility. So what do? Well, we have to incorporate in Hooke's law for torsional flexibility or a torsional spring. So what we're going to do to that is we're going to add to it Hooke's law, or a version of Hooke's law for torsional spring stiffness. So what is that going to be? Well, that's just going to be equal to, and if you recall, what's Hooke's law for torsional spring? It's T equals K phi. And so what we need is this phi term added here, right? So we're going to say plus T over K, all right? So all I've done is I've taken this phi value from Hooke's law and rearranged it by dividing by K, and I add that to my TL over JG. So it's pretty straightforward. We're going to say phi is finally going to be 30 kip inches times 48 inches divided by 10 inches to the fourth with 4,000 KSI in that denominator, plus 30 kip inches divided by that 120 kip inches per radian, okay? And so let's punch this all through and see what we get. We get 30 times 48 divided by 10 times 4,000. And so the first term becomes 0.036 radians. And then we add that to 30 divided by 120, so plus 0.25 radians. And so finally, we say phi of A. You know, we could have put a subscript A under all of this, but phi of A is equal to 0.286 radians, and of course that's going to be going clockwise. If we were to put, you know, a little viewpoint here and look in this direction, we see that that's going clockwise. Now, you tell me which term had the most impact. Well, the flexibility, so the flexible connection. So what that means for this particular problem is what happened was that connection, that flexible connection, rotated more than the shaft itself twisted, okay? So the total amount of twisting that incorporates that flexible rotation of the connection itself is 0.286 radians. Okay, so that concludes this example. If you found this helpful, please hit like and subscribe. Thanks for watching.